Hello everyone, welcome to Maths Club. Today we are going to discuss about the questions regarding volume of solid generated by rotating a bounded region about a line which is parallel to the x-axis, and here we are going to use cylindrical or sail method. So first we are going to start with an example. Here is the example. Find volume of solid generated by rotating a region bounded between the line y is equal to x and the curve y is equal to x cube in first quadrant when rotated about the line y is equal to -1. So like before, we will start by finding out the point of intersection between this line and the curve to draw the graph for both, and then identify the region bounded between them in first quadrant. To find the point of intersection between the curve and the line, we need the values of x and y using both the equation. So first we are going to equate y from both this curve. So that will going to give you x is equal to x cube, or x cube is equal to x. Now you have to solve this for the x. So take them in the same side, which gives us x cube is equal minus x is equal to 0. And if we take x common from both the equation, finally we are going to get x into x square minus 1 is equal to 0. Now to find the value of x, we have to separately equate both the factor x and x square minus 1 equal to 0. From first factor, we will get x is equal to 0, or from the second factor, actually we are going to get x square minus 1 is equal to 0, which finally gives us x square is equal to 1, which gives values of x as plus or minus 1. But here we have to be careful. We are talking about the region bounded in the first quadrant. So negative values of the x and y will not be needed. So because of the first quadrant, we can take only two values of x, that is x equal to 0 or x is equal to 1. Now to find the point of intersections, you have to put these values of x into any one of this equation, that is equation of the line or equation is of the curve. If we put x equal to 0 here, the y is also 0, and at x equal to 1, y is also 1. So we are getting the pair at x equal to 0, y is 0, and at x equal to 1, y is 1. So finally you can conclude the point of intersections between the curve and the line is 0, 0 and 1, 1. So to draw the graph, we have to start with both the coordinate axis, the x-axis and y-axis. Then we are going to draw the line y is equal to x and the curve y is equal to x cube. This line will and curve both will go from 0, 0, that is the origin, to 1, 1. And the region between this line and curve will be this portion. Let's shade the region for better understanding. Now we have to draw the line about which the region will going to be rotated, and here the line is y is equal to -1. To get the solid of rotation, we have to draw the image of this region about the line y is equal to -1. The first image of the line y is equal to x, and then image of the curve y is equal to x cube. Now to get the solid, we have to join the end of the original region and its image by the circle. This is the circle at the right end and this is the circle at the left end. Now we're going to shade the entire solid to better understand the actual figure you are going to get. So this is the solid of the rotations we are getting. Now as we need to use the cylindrical cell method to find out the volume of this region, so you have to draw a cylinder whose axis will be on the axis of rotation. First we are going to take one end of the cylinder which will be circular and which will going to lie on one curve and its image, and then we can complete the cylinder by drawing another circular end on line and its image and then joining both the circular end. Let's shade the cylinder. Now if this cylinder moves from the lowest point to the highest point, then it will going to cover the entire solid. So if we integrate the cylinder volume from the lowest point to the highest point, then it will going to give you the volume of the entire solid so formed. So to find the volume of the cylinder, we need to multiply its curved surface area with its width. So to get the curved surface area, we need the radius and height of the cylinder. As the center lie here on this y is equal to -1 line, so radius of the cylinder can be taken as this portion plus this portion. As this is the distance from the x-axis, so this portion will be y, and this is the distance of this line y is equal to -1 from the x-axis, so this will be 1. So finally we can say the radius of the cylinder r is equal to 1 plus y. Now the height of the cylinder. This portion is the height of the cylinder, and this is actually the distance between the point on the line and on the curve. Actually it is the horizontal distance, and horizontal distance between any two points can be represented by the difference of x between that two points. So you can finally write the height of the cylinder is difference of x between the line and the curve. From the curve, the value of x is y to the power 1 by 3, and from the line it is y already. So the height of the cylinder is y to the power 1 by 3 minus y. This is the figure without any shade in the solid. First we need surface area of the cylinder, which we can denote it by delta A, and by using the basic formula of the surface area, it's become 2 pi r h. We can substitute the values of the r and h, both will come in terms of y. Generally we can say when the axis of rotation is parallel to the x-axis in cylindrical method, the finally values of the r and h have to be in terms of y. One plus y, and h is y to the power 1 by 3 minus y. This is the surface area. Now we can take the width of the cylinder. Here if we take the width of the cylinder, this is a very small part. We can consider this is as delta y because y is parallel to the y-axis. So the volume of the cylinder we can write delta V as the surface area, that is delta A, multiplied by the width, that is delta Y. Substituting the values, we are going to get 2 pi 1 plus y into y to the power 1 by 3 minus y into delta y. We can expand it to get a simplified value. So after expansion, it's become 2 pi multiplying by the 1 first, y to the power 1 by 3 minus y plus taking this 2 together, y to the power 4 by 3 minus y squared delta y. Now, when the cylinder moves from the lowest point to the highest point, then it will going to cover the entire solid. So to find out the volume of the solid, we have to integrate the volume of the cylinder from the lowest point to the highest point. The lowest point is origin we have, and the highest point we have A, that is 1 comma 1. So here you can say y is varying from 0 to 1. So to find the volume of the entire solid, we have to integrate the delta V, the expression of the delta V, which you already got here, from 0 to 1. So you can write the volume of the entire solid V is equal to 0 to 1 delta V. Now you have to substitute the value of the delta V. So it's become integration 0 to 1 2 pi y to the power 1 by 3 minus y plus y to the power 4 by 3 minus y square. And inside the integral, delta y can be taken as dy. Now to integrate it, we have to use the basic formula of the integration, that is x to the power n dx is equal to x to the power n plus 1 upon n plus 1. As 2 pi is constant term, so it can be taken outside the integral. The first term become y to the power 1 by 3 plus 1 divided by 1 by 3 plus 1 minus y squared divided by 2 plus y to the power 4 by 3 plus 1 upon 4 by 3 plus 1, and y square will become y cube divided by 3. The limit is from 0 to 1. Now after substituting all the values, at 1 all the y will become 1, and at 0 all the y will become 0. So finally it's become 2 pi. This gives you 3 by 4 minus 1 by 2 plus this is your 3 by 7 minus 1 by 3. After taking LCM, I'll calculating, we'll finally going to get this is equal to 29 pi upon 42. So we can conclude here that the volume of the solid of rotation is equal to 29 pi by 42, and that's the answer. Hope you understood the procedure. In the next video, we are going to discuss the volume of a polar curve. Thanks for watching. Have a nice day.